All right, thank you, everyone. Thanks for the introduction. In this talk, we're going to introduce you to our work in examining the new large language models and their application in security vulnerability repair. So firstly, what are large language models? If you haven't already heard, which probably you have by now, is these are really large machine learning models that have been trained over billions of lines of open source code, granting them the ability to write new code. They've garnered plenty of media attention by now with things like ChatGPT and GitHub Copilot, and it seems like we can hardly read any tech news lately without being bombarded by their latest capabilities. So far, evaluation of these models has focused on their functional performance, i.e., given some programming task, how well can these models complete those tasks? The most well-known test suite in this particular space is Human Eval, which is a data set by OpenAI, which explores a model's performance in writing Python code. However, we know that it's not just their functional performance that we should be caring about. We should also be caring about their security performance. And as it turns out, in about 40% of the time in security-relevant contexts, when you get them to write code, they actually produce vulnerable code. But, crucially, these models are non-deterministic. If you run them more than once, you'll get more than one different output. So this actually raises a question for us. Given that the models can produce secure code 60% of the time, and can be regenerating their outputs to get different outputs, can we actually leverage these properties to repair identified vulnerable code? So in this work, that's exactly what we set out to answer. So we created a methodology with a repair framework that would take buggy programs which have been identified by whatever tool you want, whether that be fuzzing or static analysis, and those will point you towards buggy lines of code, which we then localize outside the box, whatever you want to use for bug localization. Once you know where the bug is, you can give that to a prompt creation engine, which will then pass that to the language models. So the way these language models work is you give them some input, and then they extend that input. They produce more code given some code as an input. I will note here that for this particular work, this was pre-ChatGPT. ChatGPT changes this a little bit because it's tuned at following instructions. The models that we were investigating aren't tuned to follow instructions, so the prompt creation was a really big research area for us. So from that, we then can merge the output of the language models back into the original files to try and get candidate repair fixes. Once you have the candidate repair fixes, you then compare them with the original security test suite that you were using, whether again that's fuzzing or static analysis, and then check to see if it passes those tests. Once you've passed those tests, great. You should also check the functionality, because the easiest way to fix a security bug is just to delete a big chunk of your program, which is not really great from a functional point of view. So we do need to pair this with functional checks as well. So crucially, as I said, because these large language models are non-deterministic, we can actually run those two middle steps, steps 2 and 3, in a loop with multiple different templates, with multiple different hyperparameters to change the creativity, the temperature, the top P, all of these parameters that large language models benefit of. We can also query multiple language models. Why not? We've got a whole heap of them now that can actually write code. So what we want to do is try as many different possibilities as possible to steer these large language models in the productive direction of fixing our security vulnerabilities. So here's a simple example just to show you what we mean. In this basic program, the user might be able to cause an out-of-bounds read by providing an index to the vehicles array, which is greater than 3 or less than 0, right? This is a really classic out-of-bounds read. So our oracle in this case is GitHub's CodeQL, which can actually point at this function and say, hey, there's a security vulnerability in here. So what we'll do is we'll use CodeQL to tell us that that's faulty, and then assemble this program into a number of prompts, which we can feed to a number of language models. We had a few different templates, ranging from a minimum amount of help, which we called no help, which basically just deletes what's vulnerable and then tries to regenerate, all the way up to something that we called commented with messages, which is essentially we take all of the vulnerable code, comment it out, and then put all of the information that GitHub CodeQL gives you into the prompt template as well, trying to steer the language model, maybe with as much information as possible to get it to come up with the most plausible fix. We then tried a number of different language models. So we had 3 of the different codex models from OpenAI. I will note that as of a few months ago, unfortunately, OpenAI discontinued the codex models, which is a little bit disappointing for us. But ChatGPT is actually built via a long chain from Code DaVinci 02, which was a model that we did evaluate. We also used AI21, which is a competing company's Jurassic J1 models. We also used the open source polycoder model, and we actually trained our own model too, which we called GPT-2 C-Source, which was trained entirely over the Debian source code base. So these are a variety of different parameters, a variety of different capabilities coming in each of these models, so that we have a really broad ensemble for this experiment. So just to give you an example of what the prompts might look like, so this is the minimum of the prompt, right? This is almost like a control. Given absolutely no help, how well will the language models actually reproduce code that's not buggy? So here, because CodeQL flagged the function body as buggy, we just throw the whole thing away and say, okay, take it away. Now, there's not a lot of context here, right? In this case, this program is very simple. So just from that individual comment, the language model probably can write enough code that we can pass. But once we get into the bigger examples, or even the real-world examples, that's just not going to cut it, because there's not going to be enough context for the language models to come up with plausible fixes. On the other hand, if we give it as much help as we possibly can, we could say, let's comment out the entire function body and say, okay, there's a bug here, take it away, come up with a new fix. Let's see how well that does as well. So let's jump straight into the results for some synthetic examples. So these are handcrafted vulnerabilities. We made them based on some previous work that we'd published at last year's IEEE S&P. And so we know that these examples aren't in their training data set, right? That's an important check for us. So what we did is we began the investigation with these handcrafted vulnerabilities. We used 3 different languages. You'll see there's Python, C, and Verilog there for a variety of different software and hardware CWEs. From those 9 scenarios, we then basically multiplied them by the number of different templates we had, and then by the number of language models we have, to get 275 different model and prompt template combinations. And from those, we then generated 10,000 candidate fixes to their different security vulnerabilities, and of those, actually about 2,800 actually repaired their programs. So that was a really nice proof of concept for us. It also really shows the power of this sort of brute force approach, where you can see that all 3 of the OpenAI models, Cushman and Da Vinci's, actually fixed all of the candidate programs, right? 100% success rate when you just keep prompting them until they eventually come up with the right fix. Meanwhile, our own language model was a little bit worse. It could only do the C ones because it was only trained over C. It did about 60% of the time. So we checked the outputs with CodeQL, which is a static analysis tool, and this is the same tool that was flagging the inputs as vulnerable as well. So we were fairly confident that the outputs it was matching were actually correct. Okay, but what about real-world complexity, I hear you say? Okay, right, so because we know that those little programs that we've done, they're small, and the crucial thing is they fit into the context window of the language models. If you know a little bit about language models, you know they have a finite input-output space. And at the time, with DaVinci O2, which was the most capable model, that was about 16,000 characters. Okay, now real-world programs are bigger than 16,000 characters. So here's an example from ExtractFix, which is a state-of-the-art bug repair, both repository of bugs and also a tool to fix them, from libtiff. Okay, this bug, when you run it through a fuzzer, will crash on line 994 of a roughly 9,000 line file. We can't possibly give that whole file to any of these language models to try and fix it. They're just not going to fit into the context window. So how do we even approach this situation? So what we have to do is incorporate a reduction step, which is where we take the buggy program and we take the patch information for that program and essentially strip out everything that we don't think will help the language models come up with a plausible fix. So the way that we did that is we said, well, okay, these are all C programs. Something relatively important for C is all of the hash includes and the libraries and the hash defines at the top of the file. So we'll keep those. And then we'll keep the entire function body up to the buggy part. And then we'll see where we are from there. And if we're still too long, which we actually were in a number of the cases, because again, these are really big projects, we'd do a secondary cutting step, which was simple as taking what we had so far and just chopping it line by line at the top until eventually it would fit into the context window, which does sound a little bit brutish, but it seems to work reasonably well. So you can see for this TIFF crop example, EFO1, we took a 9,000 line file, we got it down to about 115 to 120 lines, depending upon the exact amount of context we then put into our comment to give to the language model. So overall, that was the generic approach. So what did we end up with now when we're looking at real-world examples? Okay, so we took a number of the examples from the ExtractFix data set, and we compared them both with what the language models can do, but also with what extract fix could do, because extract fix itself can't fix all of these different bugs. So we said, okay, this is a state-of-the-art bug fixing library, and here we have language models which actually in that first column are repairing almost as many as the extract fix data set. And bear in mind, these aren't even trained to do it. These aren't models that are trained to bug fix. They're just models that are trained to write code. So from those bugs, we ended up with 432 model and prompt combinations, generated nearly 20,000 candidate patches, and came up with just under 1,000 repairs. And when we look over it, we see that about 8 of 12 scenarios were repaired. But it's not quite as simple as that, because as it turns out, when you dive a little bit closer into the results, you see that some of the fixes, which are fixes according to both the static analysis security check or the fuzzing check and the functional checks, actually don't fix the program at all. So here's an example from Cushman, which was marked correctly there. It does add a bounds check to this out of bounds error, but it also changes the variable which is accessing the array, totally breaking the program. So why was this marked as a success? Well, as it turns out, libtiff's functional test suite wasn't testing it. So we got it, so the security tester was saying it was fine, and the functional tester was saying it was fine, but it actually wasn't fine. So when we then actually compared the fixes with what we had, with the historical patches provided by humans, we found that actually our success rate reduced from about 8 out of 12 to about 6 out of 12, because the fixes that were coming out of the language models simply weren't plausible, even though the functional test suites and security test suite was saying they were. And this is actually something that Extract Fix also note in their work. This is an ongoing problem in automated programming repair. If your functional test suite isn't good, you're not going to get good results out of automated functional program repair. So for conclusions, we know now that code writing language models can be utilized for bug repair tasks. This is particularly true now that ChatGPT has come out, and we don't have to worry so much about doing the complicated prompt engineering, because the instruction models are so good at following what we want them to do. Using prompt engineering, we did come up with fixing bugs in the code, but yeah, it's maybe not so difficult as it needs to be anymore. We fixed 100% of our synthetic handcrafted examples, which we know weren't in the training data, 50% of the historical real-world CVEs, which might have been in the training data, but the fixes were different enough that we weren't too worried. Automated tooling, we proposed this framework. There are a number of limitations. We can only do single file fixes. As we said, success doesn't necessarily mean fixed. The models were better at removing and editing code than they were at coming up with brand new code, and obviously scalability concerns. We can't all just prompt 8 language models 20,000 times to come up with candidate fixes. So thanks very much for listening. I'm happy to point out that everything we did is open source on that QR code and that URL there, and I'm very happy to take any questions now. Thank you very much.
All right, we have about 2 minutes for questions. So if you have a question, you can stand over there.
I find it interesting that you found that some of the codes fixed by the large language model actually passed the test, but the fix is not there. So do you think you kind of create some kind of adversarial examples for those testing programs?
Yeah, that's a great question. And actually, this is something we're looking, I think other people are looking into it now, is trying to use language models to come up with better test suites. Because at the end of the day, you can't do anything if your functional tests are inadequate. Every guarantee you've got is just hopeless. So trying to use the language models to maybe identify if test suites aren't practical, or augment them with, let's say it comes up with a fix and a test for that fix, might be a better approach than just the pure come up with fix approach that we did.
Okay, thank you.
Thank you.
Hey, great talk. I had a question about how you trimmed large, like 900 something line of code to manageable context window. Like, how would it scale? I mean, you did it for the 12 different vulnerability cases, but have you thought about how it might scale on? Like, let's say, if you want this system to work on all types of vulnerabilities, like, can we automate that part as well?
Yeah, so that's a great question. One of the things I'll note is that we didn't do bug localization ourselves, right? And bug localization is a huge field of research, and that's a real challenge because we're relying on things like fuzzing, right? And a fuzzer might crash a program miles away from where the actual vulnerability is. So if you can localize the bug adequately, that was where we said, our framework can work because we can just sort of point it at the exact context it needs. But I will note, as we say there, we're limiting ourselves to single file fixes. So we don't want to be able to, in fact, we couldn't come up with a plausible way of presenting multiple files to the language model because they only work over sort of a single point in space for editing. So this is a sort of question that I think still remains to be answered.
Thank you.
Thank you.
So you had an ensemble of different large language models trained in a variety of different ways, but I don't think I saw you comment on how one worked better or worse than the others. Was there any interesting finding there?
Yes. So the OpenAI models performed best. It wasn't even close. The Cushman model performed best on the real-world fixes minus the plausibility checks, and then once we did the plausibility checks, the Da Vinci models performed best. Our own language model, which is, we can only really comment on how well the two open source models did, which is our one, which only had 700 million parameters, and Polycoder, which had 2.7 billion. Our model failed to generate really any good fixes. The only one it did fix, which was EFO1, the bounds check, we actually did a dive into its training data and found the fix in the Debian source code. So we were like, okay, well, that one doesn't count. There's a chance that the Da Vinci models have that benefit as well, but of course they don't actually tell us what they're trained over. So while they might be benefiting from the training data, the only thing we could do was compare the fixes they generated with the human fixes. And, we saw fixes that weren't the same, but were still plausible. So we said, well, it's not really strictly reproducing if it is training. So yeah, it's a difficult one to say. Obviously, the more parameters you have, the better. The bigger your training data, the better. All the things that we expect. Yeah.
Thank you.
Thank you.
This is the last question. Yeah.
Thanks. Hi, this is Quinson from George Mason. So great talk. So when you mentioned this limitation for this single file fix, do you mean this? Can you deal with this multiple function? So for this vulnerability.
So I'll clarify. It's a single file, single location in the file as well. What we were trying to do was prevent having to deal with huge bugs that are really far apart, because then you need to work out how to give that all in the context window. And we're limited to that 16,000 characters. And that only one model could do 16,000 characters. Our own model could only do 1,000. So you really have to have very localized bugs, and that was how we chose the extract fix bugs that we chose out of the larger data set. We only used however many it was out of the broader extract fix, because we were focusing on those bugs that only were localized. They only needed a few lines to be edited in a specific location in the code.
So do you mean it's still focused on single function mainly, right?
Yes, single function as well. Yeah.
Thank you.
Thank you.
All right. So let's thank our speaker one more time.
Thanks.